Okay, I will begin. Okay, so last time we were talking about vector bundles, and we started by talking about local vector bundles. In the picture, I said that you should have in mind of a local vector bundle is some open subset of a locally convex space, and then attached to every point in the open subset is another copy of is a copy of another locally convex space, and all of the ones that are attached here are the same. I'm drawing them like the open subset is in a two-dimensional vector space, and the vector spaces that I'm attaching at each point are one-dimensional, but of course either thing could be infinite dimensional and different. Okay. Like so. Okay, so that's the picture you should have in your mind about what a local vector bundle is. And then we talked about vector bundles. And vector bundles were manifolds where the manifold structure was specific in the sense that all of the charts took values in a local vector bundle. Okay, so a local vector bundle we denoted with um, three elements. So it was a U, let's see, sorry, I think, let me just make sure I call it the same thing as I called it last time, sorry. Right, so I denoted them like this, okay? All right, so it was a V0 and an O and a V1, okay, and O was a open subset of V0, okay, so that's my O here, and my V1s were some locally convex space attached to each point. Okay, so that was how I denoted a local vector bundle. And then we talked about local vector bundle maps. So they're maps between two local vector bundles. And I'm not going to redraw the picture. I spent some time with it here. So I have a local vector bundle here and a local vector bundle here. And the idea of a local vector bundle map, which I denote by phi, is that there's a map phi 0, which maps, right? So which maps a point x to phi 0 of x. And so each point here gets mapped to a point in the image local vector bundle. And then if I take the vector space, which is attached to a point here, and the vector space, which is attached to a point here, the local vector bundle map assigns a linear mapping from this vector space into a continuous linear mapping from this vector space into this vector space. So that's what a local vector bundle mapping is. All right, then we said that a vector bundle is a manifold, all of whose atlases, which possessed an atlas, all of whose charts were local vector bundles, and all of whose overlap maps were local vector bundle isomorphisms. Okay, so that was the idea of a vector bundle. So now what we want to do is we want to see what you can do with vector bundles. So what kind of structure do vector bundles possess in general? Okay. Um, so we make a definition. Okay. And the definition a priori doesn't make sense. So one of the things we'll have to do is verify that everything I say makes sense. All right. So let E, so typically you denote a vector bundle by E. Okay, so let E be a CR vector bundle. Okay, so again, that means it has an atlas of vector bundle charts for which the overlap maps are vector bundle isomorphisms. Okay. All right, so we're going to construct some, and so here R, as usual, is like so. Okay. All right, so um, the what's called the base space of E. Okay, so the base space is going to be kind of like these open subsets here. Okay, but you have to define it a little bit carefully. Okay, the base space of E is um, the set of points E, little e, in E, such that um, there exists um, a vector bundle chart. Okay, so there's this terminology admissible charts, and I'll stick with my sort of lazy convention of not saying admissible, and I'll just say a vector bundle chart. And it's understood, of course, that it's admissible. So if there exists a vector bundle chart, okay, so a vector bundle chart is comprised of four things. Um, one is an open subset of E, it turns out to be an open subset of E, which I write as V. Okay, um, and that's the chart domain. Okay, and this is the chart map, just like a normal chart, except I'm using V rather than U to denote the chart domain. And then the chart codomain for a vector bundle is a product. And it's a product in the same way as for local vector bundles. I have this product structure of O cross V1. Okay, all right, so it's V psi 0 cross V psi 1. Okay, so that's what a vector bundle chart was. So this was part of our definition of a vector bundle that we talked about last class. Okay, so there exists a vector bundle chart so that, okay, psi of E, okay, so psi of E is going to be a point in V psi 0 cross V psi 1. Okay, and so again, you should think of this as being these guys, and this as being these guys. All right, and so we want the points which are 0 here. So the points where they attach to O. All right, so it's X O. All right. Sorry, X0, not O. Okay. All right. All right. Okay. Good. So that's what the base space is. Okay. Um, and the base space is, as we will see, it's a manifold. In fact, a submanifold of E. And so we're going to denote typically the base space by manifold-like symbols like M. Okay. Okay. Um, So now there's also a vector bundle projection, okay? And so there's immediately a potential question that arises here, and that is, does this definition make sense? So the definition is that it's the set of E's where there's some vector bundle chart, so that in that vector bundle chart, E maps to a point x0. Okay, so is it true that if it maps to a point x0 in one vector bundle chart, then it'll map to x0 in any vector bundle chart? The answer is yes, but you have to prove that. Okay. The next thing, the vector bundle projection, okay, is the mapping. And I'll call it pi from E into M. Okay. And it's defined by the following thing. Okay. So okay, so let's take a point E in E, okay, um, and take a vector bundle chart. Okay, about E. Okay, so a chart that contains E, and define. All right, so pi of E, okay, is going to be, all right, so what you're going to do is you're going to take the point E, and under the chart, you're going to map it to a point in here. Okay, so it's going to be when you map, and so I'll write down something that I have in the back of my mind as I'm writing this formula down, and then I'm going to maybe erase it. Okay, just so it makes sense to us. So psi of E is going to necessarily be a point in there. Okay, so it's going to be a point of the form x comma E prime, let's say, okay, in V psi 0 cross V psi 1, okay, and therefore x is equal to PR1 composed with psi, okay? All right, and what I want for m to be is the point in m, pi v, the point in m should be x0. Okay, so what I'm going to do is I'm going to take psi inverse of x0. Okay, so let me maybe write that here. Okay, so we're going to take psi, and so let me say that pi of E is going to be psi, because I want to go back to the manifold now. So psi inverse of x0. Okay, so that's where this formula that I'm about to write down comes from. Okay, so it's psi inverse of PR R1 composed with psi of E0. Okay, so that's the definition. And so we'll have to make sense of that somehow. All right. Okay, so just like the previous case, the problem might be that this definition of pi isn't well defined. Okay, so it could be well defined because the base space isn't well defined, so we have to prove that. And then we have to prove that this definition of pi is independent of the chart. Okay, all right. So that's another construction. And so again, we have to make sense of these constructions, but we'll do that. Okay. For x in M, pi inverse of x. Okay, so pi goes from M E to M. So pi inverse of x is the set of all points that map to x. This is called the fiber. Over, let's say, the fiber of E over x. Okay. And then finally, yeah, well, let's let me say this. Okay, if I take a subset A of M, okay, I'm going to denote E restricted to A to be pi inverse of A. Okay, so this is basically the set of all fibers, okay, over points in A. All right, so those are some definitions. this thing that I just wrote is called the restriction of E to A. Okay, so then now, like I said, the thing we have to do is we have to say, um, we have to prove that all these things make sense. Okay. All right, so let's do that. Okay. All right, so let me write sort of a short version of this. So the base space, um, the bundle projection, and fibers are well defined. Okay, so now it's easy to see why these things are true. Um, it's a little uh, less easy to prove it because it requires fiddling with charts. Okay, but let's do that, or at least let me maybe chat my way through a proof of that rather than sort of writing down a whole bunch of symbols. Okay, so base space. Okay, so why is the base space well defined? So what it means, as I said when I wrote this down, it could be that you take, so we want the points in E, which in some vector bundle chart look like this. Okay. And so you should verify that if it looks like this in some vector bundle chart, then it'll look like this in any vector bundle chart. But the reason why that's true is clear, and that is that vector bundle charts are linear in the second entry. Okay, so since um, I should say the overlap maps for vector bundle charts are linear in the second entry. Okay, so since overlap, that's a property of local vector bundle maps. Okay, since the overlap maps for vector bundle charts are local vector bundle maps, they're linear in the second entry. So what this means, so that's a point E in E that for which psi of E is x0 in some vector bundle chart. Uh, V psi V psi 0 V psi 1. Okay. Will satisfy psi prime of E is equal to x prime 0 for any vector bundle chart. Okay. And that's just because linearity will ensure that the 0 here is mapped to 0 there. Okay. So the base space makes sense. Projection. Okay, so the vector bundle projection should make sense. So the story here looks rather the same as it does for the making sense out of the base space. And why is that? Um, and it's because, again, it's because the overlap maps are local vector bundle maps. And what's the upshot of that? Well, going back to my picture here, the upshot of that is that points in, sorry, let me do it in the forward direction. Points in this space are mapped to points in this space, okay? And the projection is the mapping which sends a point here to the point X. Okay, so because the point X in the product is X comma 0. Okay, so it takes a point in here, which may be, takes a point in here, which may be X comma E, and it maps it to the point X comma 0. Okay, that's what the vector bundle projection does. Right? So let me see if I can write down some words to make sense out of that. Okay. So since local vector bundle maps, creating my L's. Um, Again, are linear in the second component. Okay, points of the form X E. So let me see how to write this in the best way. Points E in E mapping to, okay, so it's going to map to X comma, let's write it as maybe E prime by a vector bundle chart. V psi, V psi 0, V psi 1. Okay. Are mapped by the overlap map to points so the overlap map is going to be some map, and I'll just call it capital psi. Okay, so in the first component, since the overlap map is a vector bundle map, the first component is just going to be some function of x. Okay. The second component, so maybe let me call that psi 0. The second component is going to be, okay, a linear function of x that depends only on, or sorry, a linear function of e that depends only on the point x that the point e resides over. So in other words, as I vary e here, and that should be e prime, okay? So as I vary e prime here, so that this remains fixed, then e prime here is going to change, but this point will remain fixed. And so the point is that this point is well defined, independent of it's defined by E, okay, independent of the vector bundle chart. Okay, so thus points x0 are independent of the vector bundle chart. And those are exactly the points which are the image of E under the vector bundle projection of vector bundle chart. Okay. All right. So, again, I'm saying in words things which could be said a little bit more precisely, but also a little bit less clearly in symbols. Okay, and then now the fact that fibers are well defined is clear. Um, so the point is that this projection here, with this projection, you take the pre-image of a point under the projection, that's going to be the set of all points which are of the form in a vector bundle chart, x e prime for some e prime, and those are the form of that point. In other words, it's fixed here and variable here. That's the same if you change the vector bundle chart, right? So it's fixed here because x is fixed here, okay? And then it's only as e prime varies, okay? Right, so fibers are also well defined basically by the same argument. Okay, so like that's the sensibility of those definitions. Okay, and really, the definitions make the fact that these things are independent of vector bundle chart, it follows pretty obviously once you understand what a local vector bundle map looks like. Okay, so the key thing is it maps all points here to points here. Okay, and it maps a point here to a point here. Okay, so a zero vector to a zero vector. Okay, that's the key thing about a local vector bundle map. All right. Good. So let me say some slightly more. So this makes sense of the definitions. Let me say a few more things. So again, and so the way you, since everything now makes sense, the vector bundle projection and the base space, the way you often write a vector bundle is you write it as like that. Okay. And the reason it's all really defined by E. Once you have the vector bundle structure for E, then M and the vector bundle projection are defined. But it just allows you to name the base space. We're going to call it M. And it allows you to name the projection. We're going to call it pi. Okay. So very often you write a vector bundle like this. Sometimes you see uh, vector bundles written like this, or some permutation of this notation. Okay. Again, it collects all the data together, so it's all fine. Okay. But sometimes you see that notation used. All right. So we know that the base manifold now is well defined. Moreover, um, M is the base space is actually a submanifold of E. Okay. Um, all right. The fibers have a well-defined locally convex structure. Locally convex topological vector space structure. Okay. All right. Okay. All right. So the fibers, so again, this is entirely consistent with our picture of a vector bundle. Okay. Sorry, a local vector bundle. So in the local vector bundle, it's actually a product, right? So it's O cross V1. Okay. And what I'm saying is the local vector bundle version of the result that I'm looking at says first that O is a submanifold, but that's clear because O, this thing sits inside V0 cross V1. Okay. And this is a submanifold of the product, and this is an open subset of this. So therefore, this is a submanifold of the product. Okay. So that's the submanifold part, the base space being a submanifold part. And then, of course, in this case, it's clear that the fibers, so these are the fibers. Okay. The fibers have a well-defined locally convex topological vector space structure. Well, they're just all equal to V1, and so obviously they do. Okay, so we just have to extend that picture um, um, uh, to vector bundles, not just local vector bundles. Okay, so to show that something is a submanifold, what do? You you show that around every point there's a submanifold chart. Well, that's actually given to us just by the definition of the base space. Okay. All right, so let X be a point in M. Okay, so M is certainly a subset of E. Okay, and so, and let psi, psi, V psi 0 cross V psi 1 be a vector bundle chart around X. Okay, so then psi of M, okay, intersect V psi. Okay, so the set of points in my chart domain, which are contained in M. Okay, all right, what's the definition of this? Well, the definition of the base space is exactly that the points in here, which are in the chart domain, are precisely the points which map to points of the form something, comma, 0. Okay, so this is psi of V psi intersect 0 cross, oh, sorry, the other way around. V psi 0 cross 0. Okay, so this is a subspace of course of V psi 0 cross V psi 1. Okay, and in fact, it's a closed subspace because when I write product here, I'm assuming that this has the product topology, and in the product topology, the components are closed um, um, because it's the preimage under the second projection of this closed set. All right. Okay, so because our definition of a submanifold, remember, required that the subspace that this thing maps to the subspace that you use in this verification has to be sequentially closed. So here it's actually closed. Okay. Um, and so the point is, it shows that this vector bundle chart is actually a submanifold chart for the base space. Okay, good. All right. Okay, so now we're going to show that the fibers have a well-defined locally convex structure. Okay. Um, all right, so again, let's let X be a point in M. Okay, and let again V psi V psi 0 cross V psi 1 be a vector bundle chart about X. Okay. All right, so let's write pi of pi inverse, sorry, not pi, sorry, psi of pi inverse of X. Okay, so what's this going to look like? So this is going to be the set of all points in E, okay, well, or in this chart domain, which when I represent them in the vector bundle chart, look like uh, um, the same point, all right? So the image of this point under the vector bundle mapping, and then the second component is going to be arbitrary. Okay, so the point is this is going to be, um, uh, it's going to be, let's say, x prime cross v psi 1. Okay, so this is going to be a subset of v um, psi 0 cross v psi 1. All right. So that's the definition of the fiber, right? So in the local vector bundle chart, in the vector bundle chart, it's the set of all points which look like this. And x prime is just going to be some, it's going to be the image under the, so let me write it like this. So where x prime 0 is psi of x, like this, okay? Right, so because I know that x is in the base space, and so when I map it under a vector bundle chart, it's going to look like this for some x prime, okay? Okay, good. So therefore, so since psi is in particular, is a homeomorphism. Okay. Okay. So I should say a homeomorphism onto its image. In V psi 0 cross V psi 1. Okay. The fiber pi inverse of x inherits the locally convex structure from V psi 1 from V psi 1 under the map um, uh, okay, so I'm going to take the fiber. I'm going to take a point in there. I'm going to map it to psi of E. Okay, but I know that psi of E is going to be a point in here. Okay, so it's going to be a point, it's going to look like x prime E prime in V psi 1. Okay, all right, so I have this mapping, which maps the fiber into this vector space. And I know that that mapping is, first of all, it's a bijection. Okay, and it's a bijection because the chart map is a bijection. Okay. And I know that it's continuous, and I know that it's continuous because psi is continuous, all right? And so what topologies do things have? Well, this has its natural locally convex topology, and what I'm saying is the topology that we're going to put on here is going to be the locally convex topology that it inherits by this map, okay? All right, so therefore the locally convex topology here defines a locally convex topology here. So the only thing that you need to worry about now is that the locally convex topology on here, maybe it depends on psi. All right, so you need to make sure that that's not the case, but that's clear. Okay, so since local, sorry, since overlap maps for vector bundle charts are local vector bundle isomorphisms. That's the definition of a vector bundle. And since local vector bundle isomorphisms have the form, okay, so they have the form x prime e prime maps to, let's say again, psi 0 of x prime, okay, and psi 1 of x prime e prime. Right, so that's what a local vector bundle map looks like. And if it's a local vector bundle isomorphism, moreover, this is the definition of local vector bundle isomorphism. It means that for fixed x prime, the mapping e prime maps to that thing is a isomorphism of locally convex spaces. Okay, where e prime maps to psi 1 of x prime e prime is an isomorphism of locally convex spaces for each x prime. Okay. All right, so there's a big long sentence. All right, so since overlap maps are local vector bundle isomorphisms, and local vector bundle isomorphisms have this property, that this mapping is an isomorphism. This means that the locally convex topology that I get on here, whoops, on here from here will not depend on the chart, because if I choose a different chart, um, the overlap map will give me an isomorphism of locally convex spaces from this onto, whatever the locally convex space is for the other chart. And so the topology for this, locally convex topology for this, will be the same. Okay. So the locally convex topology of phi inverse of E fiber is independent of chart. Okay. All right. So again, none of this is difficult at all. It all just rests on the basic properties of local vector bundle maps. Okay, so in other words, what this says is that this picture here isn't such a crappy picture of to have in mind about what a vector bundle looks like. So it's a base space, which in my picture I've represented by this, and then some fibers that I attach to each point. Okay, that's the picture. That's a good picture of a vector bundle. Now, it's important not to oversimplify the picture, to have this as um, uh, so this is true locally for every vector bundle, kind of by definition of a vector bundle, but it's not true globally. So let me say what that means. Okay. So, all right. So, um, well, vector bundles locally look like um, base space times fiber. Okay. This is not generally true globally. I didn't let me give you an example, and I'm not going to work the example out in any kind of detail. I'm just going to draw some pictures and sort of convince you why it might be true. So I'm kind of assuming that you've run into the notion of a Mobius strip. Okay, so what's a Mobius strip? So a Mobius strip is, you can build one out of cardboard. And how do you do it? You take a strip like this, okay, and you match the edges, okay? And if you match the edges so that they have the same orientation, then you end up with a cylinder like this, okay? However, if you match the edges with the orientations reversed, okay, so I glue this point to this point and this point to this point, okay, then I end up with something that's not a strip or a cylinder, but it's a Mobius strip, okay. Um, so that's what a Mobius strip is. And like I said, I'm assuming that as mathematicians or people, um, interested in mathematics, you've run across a Mobius strip, and Mobius strips, have this property that they're not orientable, so there's no kind of inside and outside to them. Okay, so what we're going to just make a vector bundle picture out of this. Okay, so let's consider the Mobius vector bundle. Okay, so here I do exactly the same thing, except I want, not a strip like this. I want to, okay, take, okay, so this thing is 0, 1 cross R. Okay, so this is 0, 1, and this is R. Okay, now you can do exactly the same kind of gluing process that I talked about here, except now, these things aren't, truncated here, right? They go off to infinity in that direction and off to minus infinity in that direction. But nonetheless, I can glue points on this edge, 2 points on this edge. And if I maintain the orientation, then I'm going to get an infinite cylinder. Okay, so I'm going to get, all right, something like this. All right, so, but again, this thing goes off to infinity in this direction, goes off to infinity in this direction. And this thing, excuse me, is basically S1, okay? Because when you glue the edges of an interval to each other, as I've done here, you get a circle basically, okay? Across R. All right. But now, if you again glue the edges, but change the orientation, okay, so right, so this point, so this point will be identified with this point when I glue, okay, and this point will be identified with this point, okay, but this point will be identified with this point. All right. Then I get some, and I'm not going to attempt to draw the picture. Okay, you get a twisted cylinder. Okay. All right. And so this thing, which is not a product like this thing. Okay. So this is not a product. Okay. So the point is that the product picture of a vector bundle, so again, I'm going to go up here. Okay. That you get here. Okay. Product of O with V1. Okay. That picture is locally valid. Okay. And it's locally valid here, right? So if you take around any point, okay, around any point, okay, this thing is going to be a product. All right. But it's not going to be a product globally. All right. Okay. So that's an important caveat about vector bundles. And so vector bundles like this, um, uh, like this, these are called trivial vector bundles. Okay. And trivial here means that it's a product. Okay. And these are non-trivial. Okay, so they have some global structure which does not come to you from the local structure. Okay, so locally these two vector bundles look the same. Okay, but globally they're different. All right. That's one of the important things that happens in geometry is sometimes your local picture does not hold globally. Okay. All right, so that's basic stuff about vector bundles. Let's maybe, so these are some, kind of slightly imprecise examples of vector bundles. Um, let's, um, okay, so, oops, sorry. So example. And so let me give a precise definition of what I mean by a trivial vector bundle. Okay, let M be a CR manifold. And let V be an F locally convex space. And so it's a vector space, it's an F vector space, whatever F is, R or C. Okay, so the um, trivial vector bundle, trivial vector bundle with base space M and fiber V is simply the product. And so it's, so I told you here the trivial meant that it's a product. Okay, so now I'm just defining the thing to be a product. Um, okay, so what's the vector bundle structure? Okay. Um, so just because I write this thing down like this, that does not tell me just right off the bat what the vector bundle structure is. Okay, so I need to define the vector bundle structure. So um, a vector bundle atlas is given by, all right. Um, so what are the vector bundle charts going to be? Well, they're going to be U cross V. Okay, so let me write it down and then I'll tell you what it all means. Okay, phi cross identity on V, and then V phi cross V. Right, so that's going to be my vector bundle charts for my vector bundle atlas, where U phi V phi is is a chart for M. Okay. All right, so that's going to be my vector bundle atlas, right? So this certainly this covers, this the set of all things which look like this, where U is a chart from for M. Okay, so if you run this over all charts for M, these will certainly cover M cross V. Okay, just because this covers M. All right. um, Note that the overlap map for charts. All right, so if I have two of these vector bundle charts, so let's say U V1 cross, maybe let me save myself some writing, VA cross VA cross identity, and VA cross V. Okay, so I have two of these. Okay. Is, okay, so it's going to be, so it's going to map from the V1 of U V1 cross V. Okay. So this, notice, is V1 cross identity of U V1 cross V. Right. So in other words, this is the image of this one under this chart map. Okay. So it's going to take a point in here, and the point in here is going to look like X comma V. Okay. And it's simply going to map it to phi 2 composed with phi 1 inverse of X V. Okay. And this is a point, of course, in phi 2 of U phi 2 cross V, and this is phi 2 cross identity V of U phi 2 cross V. All right, so it maps from the image of one chart domain to the image of the other chart domain. And the point is that it leaves the vector part of the vector bundle unchanged. Okay, so that defines the vector bundle structure. And so you'll notice that the trivialness of this vector bundle comes from the fact that the overlap map doesn't do anything to the vector part. Okay, it's the fact that the overlap map might do interesting things to the vector part that leads to a phenomenon like this. Okay. All right. Okay, so this is sort of in general what a trivial vector bundle looks like. All right, good. So now let's look at vector bundle mappings. So you won't be surprised to know what vector bundle mappings are. Okay, so if a vector bundle is a manifold that locally looks like a local vector bundle, okay, a vector bundle mapping is going to be a mapping that whose local representative is a local vector bundle mapping. Okay, so um, the construction is by grammar. Okay, so okay. All right, so let me take two vector bundles. Okay, so E over M and F over N. So a mapping. B from E to F is a CR So let me say CRF mapping is a CRF vector bundle mapping. Um, with the property that for each E in E, there exist vector bundle charts. Okay, so there's going to be one about E and then one about phi of E, just like you have for mappings, right? So for mappings, you have charts about E or about X and phi of X, and then you write down the local representative. Okay, so you do a similar kind of thing here. All right, so vector bundle charts, V psi, psi, V psi 0 cross V psi 1 about E. And then another vector bundle chart about phi of E. And let me call this one W, not psi, obviously, kappa, kappa. Then W, vector space W, kappa 0 cross W kappa 1. Okay. About phi of E. Such that. Okay, so we're going to build the local representative, and to build local representatives, you need for a property like this to hold. Okay. So once you have that, then you can build the local representative. And the spared you a loud cough. And the local representative, so phi psi kappa is a local vector bundle map. Okay, so that's the definition. So the idea is, and so sorry, I'm going to scroll way back up to the last lecture because I don't want to redraw this complicated picture. Okay. The idea is that I have two vector bundles. One locally looks like this open set Cartesian product with a vector space. And then this one is local open subset of locally convex space, Cartesian product with vector space. Then I have a mapping, which is a local vector bundle mapping. So if my vector bundle E over M locally looks like this, and my vector bundle F over N locally looks like this, then a mapping from E to F is a vector bundle mapping. When its local representative is a vector bundle mapping, just like in this picture. Right? So it's as simple as that. Okay. All right. So that's the definition. And just like vector bundles come equipped with structure, um, vector bundle maps come equipped with structure. Okay, so if phi from E to F is a CRF. That's a horrible looking F. Vector bundle map between CRF vector bundles I E to M and I F F N, then okay. Um, there exists a CR mapping, phi naught, from M base space to base space. Right, just like in our local vector bundle picture, we had a mapping phi naught, which mapped the open subsets to the open subsets. Okay. Such that and a nice way to view this is with a diagram. Okay, so I have phi, which maps E to F. Then I have the two projections. Like this, okay? And this picture kind of encodes the, and so again, I apologize, I'm going to scroll back up to here. All right. So local vector bundle maps map fibers to fibers. Okay, so would they have a property which you would call fiber preserving, right? So it takes this fiber here and it maps it to this fiber here. And so this diagram you should read as saying fibers are preserved, because that's exactly what it's doing. It's saying that if you take a fiber over a point in here, okay, so you're going to take the pre-image of a point in here, which is going to be the fiber, and you're going to map it forward here and then project it down, then it's going to map to, so if you have a point X here, it's going to map to the fiber over phi naught of X. Okay, that's what this diagram tells you, is that the fiber of X is mapped to the fiber of phi naught of X. Okay, so this zero diagram commutes, and it's more, so this is just fiber preserving, but it's more than just fiber preserving. And the mapping phi sub x, which is simply phi restricted to the fiber over x to the fiber, sorry, E. Sorry. All right, so this is the mapping from the fiber over x, i.e., to the fiber over phi naught of x. So this mapping is continuous linear. Okay? Just like it is in the local picture, right? Okay, so that's what a vector bundle map does. Okay, and this is obviously true because it's true locally. Okay, to verify. So this, sorry, the existence of this mapping um, is defined by the fact that the local representative is a local vector bundle isomorphism. And so it's going to map, sorry, not a local vector bundle isomorphism, a local vector bundle mapping. So it's going to map points in the base space here to points in the base space here, right? So that's how this mapping exists and is well defined. Okay. Um, And because phi, the local representative of phi is a local vector bundle mapping, um, um, and the local vector bundle mappings map fibers continuously and linearly to fibers, then phi itself must be continuous and linear. Okay, so I'm not going to prove this because it's more or less just follows immediately from the definitions. Okay. All right. Um, okay, so I think let's see. Yeah, I'll do just one tiny little thing, which is that I take it back. I won't do that. So next time, what we're going to do is we're going to talk about building vector bundles from existing vector bundles. So, and we'll have a few ways to do this. One way is to talk about the notion of a sub-bundle. Okay. And sub-bundles are to vector bundles as submanifolds are to manifolds. All right. So it's a subset of a vector bundle, which is itself a vector bundle. All right. So that's one construction that we'll talk about. We'll also talk about ways of taking vector bundles and combining their fibers, basically taking products of the fibers. Okay. So there's a few ways of describing vector bundles like that. Um, and so these are kinds of analogous to things that we've talked about in calculus and geometry, products and sub things. Okay, so those are natural. But then there's a new, very particular vector bundle construction, which is called a pullback bundle, and so we'll talk about that as well. Okay, so that's what we'll do on Wednesday. And so unless there's questions, I shall sign off.